So we know that the value of stress is equal to P divided by A, correct? P depends upon the applied load, right? And it is equal to the applied load. It is the internal resistance which is equal to the applied load, correct? And A is the cross-sectional area or geometry. A cross-sectional area depends upon the geometry. So we can safely conclude that the value of stress depends upon the applied load and the cross-sectional area or geometry of the body, correct? But if you recall, if you remember, I made a simple graph like this. I made it here to be precise. At this point of the whiteboard, I made the graph. And what I told you, that the value of stress applied can change depending upon the value of P, depending upon the value of A. But for every material, there is a safe limit of stress which it can sustain, which it can bear, beyond which it will fail, it will break, it will crack, it will fracture, right? There is a limit to how much stress it can bear, and that is why I told you that stress is a better parameter, a better indicator of strength and not the load, right? This discussion we have already done when I was telling you about critical sections, right? You remember? If you don't remember, you are not revising. You must go back, check the lecture and keep revising. So, stress is a better parameter of how much strength a material has and how much stress value you can increase safely. Increasing of stress value means increasing of load for a given specific area, right or not? And that value of how much stress a material can bear is a property of the material. It depends upon the material. Some materials can have a higher value of stress, means some material, let's say, I'm just giving you some random numbers right now, don't think much about it. Suppose some material can bear up to 200 megapascal of stress safely without cracking or breaking or fracture, while some other material may bear less than that, maybe 175 or 170 megapascal of stress. So this is a property of the material. It is different for different materials. Aluminium will crack, will fracture, will break at a different value of stress. Cast iron will break at a different value of stress. Copper will break at a different value of stress. Steel will break at a different value of stress. So all of them will have different values, right? So if you have a component, if you have a bar on which same load P you are applying, cross-sectional area is also same. This is bar 1, this is bar 1, let's say of aluminium. Correct? Then there is another bar, looks exactly the same cross-sectional area, same load P you are applying, but this is of steel, let's say. This is of steel. How much will be the value of stress in both of them? Value of stress, same, P by A. Because stress depends upon load and geometry. Load is same, geometry is same. So stress is same. But how much maximum stress they can bear without fracture, without cracking is going to be different. It is going to be different. Let's say at this point of time, again I am putting random numbers, maybe steel can bear up to 200, but aluminium can bear up to 175. Which means that for the same dimension, for the same area, the steel one can bear more load, right? If sigma is equal to P by A, you keep increasing the value of P for the same cross section, sigma will increase. Both of them will have same sigma, but as soon as load you are increasing, sigma is increasing, 50, 60, 100, 150, 175, as soon as it will reach 175, if maximum stress that aluminium can bear is 175, it is going to crack and fracture at 175. this will still hold on, this will not fracture at 175. This, as I showed you here, may go up to 200 and it will fracture and crack at 200. So you realize what is the difference? There is a difference between this sigma, which is simply how much stress is being applied, versus maximum sigma, safest, highest value of sigma, which any material can bear safely. These are two separate things. This is a very basic thing that I am teaching you, but it is important for you to know that one sigma, the value of stress which exists in any material at any point of time, depends upon load and cross section or load and geometry. But how much maximum it can take, that is its property. Some may take 100, some may take 500, some may take 200, some may take 300. Got it? Don't think these are the accurate numbers. We will be discussing the accurate numbers as well. I just took simple examples and simple values for your understanding. So, how do we now know that how much is the maximum value for steel, for aluminum? How do we know that? The value of sigma which you are applying, that you can calculate. How? How much load P is there? Divide with the cross section, you got the value of sigma. But how much is the safest value of sigma? For aluminum, for copper, for steel, for cast iron, that you have to experimentally calculate. You cannot do that by any guesswork or by any formula as such. You have to do experiment. You have to take the material which is made up of aluminum or steel and apply the load and calculate that at what value of stress it is fracturing, it is cracking. And that is how experimentally you can determine that this much is the safe value of stress for this material. And to do that, we have to conduct test, and that test is called as tensile testing. Name itself is telling you that we will take a specimen and we will put it on a machine, and the machine will apply the tensile load and machine will calculate that at what value of stress it is cracking, fracturing and breaking. And that's how you decide how much is the safe value of stress for any given material. Got it? So the tensile test is performed on a machine like this. This machine is called as Universal Testing Machine, in short UTM. I'm sure you would have seen some version of this machine in your college lab. If you are a mechanical engineer and you visited your lab assignments, you have done your assignments, so there you would have seen a machine like this. Different versions, it may not look exactly like this. There are different shapes, means different colors and sizes in which this is available, but this is the general shape. What exactly is going on here? What is the, in this entire machine, the thing that we need to focus upon are this end and this end. What is this? This is the lower end which is fixed, and this is the upper end which is movable, which can be moved up or down. Okay, this can be moved up or down. What exactly we do here? In the gap between them, we put a specimen. This is a specimen. Okay, this is not the real size. Don't think that specimen looks this big. Specimen is going to fit here, is going to fit here. This specimen is going to come there. Okay, so its dimensions are not that big, it's small. I will discuss about the dimension, but realize that this specimen is not as big as the machine. It is small. The specimen is small. I have shown it larger so that you can easily see it. This specimen, as you can see, has some screw type setup at the ends, right? Generally it is kept because it is going to fit on these ends, at the top and the bottom end. Also means it is made also slightly enlarged so that it can be gripped properly here, because what we are going to do, this specimen will be kept here, it will be fixed, it will be properly mounted there. The lower end will be fixed, it will not move, but the top end will start moving in the upward direction. So as a result of that, what will happen? If you grip it from the bottom, but you start pulling it in the upward direction, so overall a tensile force is going to come, a load is going to come, a tensile load is going to act on this specific specimen, as a result of which it will start elongating, its length will start increasing, and that is what the experiment is all about. You apply the load, it will start elongating, and at some point it will fracture, it will rupture, it will break. And as I told you, that we want to measure different values of stress, that at what stress what is going to happen, and eventually at what stress it is going to crack or fracture. Got it? This is the purpose of this machine. Now, how much, what is the size of this, how much is the dimensions of this, all these things are generally standard, right? You cannot just pick any specimen, you are not going to find any random specimen. These specimens come in standard dimensions and they depend upon country to country. Most of the countries use different dimensions, but the most popular one is ASMT standard, American Society of Testing and Materials. You don't have to write any of this. Whatever I am explaining so far, do not write any of this. It is just for your own understanding. You don't have to draw or write all of these things, okay? So ASTM is one standard, like we have different system for calculation, for measurement. Similar is the setup here. Different countries use different standards, different dimensions of specimen. Most common one is ASTM standard, where shape is cylindrical. This is cylindrical. Its length is 50.8 mm. Acha, one more important point. Length means how much? There are marks made on this entire specimen. There are 2 marks, and between those 2 marks, what we measure our length. We don't measure our length. We don't measure our length for the entire specimen. Why? Because this part is going to be gripped. That is why it is made bigger, so that it can be gripped properly. And if you remember, in theory, Saint Venant principle means in calculations, in our discussions, we may not consider Saint Venant principle, but in actual material, it is going to be there, right? So the value of stress becomes uniform when it is away from the end. We discussed this, right, in Saint Venant principle. So at the end, at these ends, the stress will not be uniform. But as you move away from the end, stress becomes uniform. So this is something where we want uniform stress, right? We are defining a single value of stress for the cross section. So we don't want fluctuation of stress. That is why end points we want to, means this length what we are measuring, we want to keep it away from the end points. That is why we don't define the entire specimen length. We place 2 markers. We place 2 markers, right? And the length between them is what we measure. It is called as gauge length or gauge length. You keep this word in mind. Gauge, G-A-U-G-E, and gauge. Both of them are same, okay? Both of them are same. Sometimes written as gauge, sometimes written as gauge. And this term you will see in fluid mechanics as well. Basically, it means measure. In simple language, simplest language, it means measure. So the distance between them is L0, which is called as gauge length or gauge length. This you can write in your notes. Okay, this you can write in your notes. So we don't take the entire length, this length only we take. Okay, and as I was telling you, for ASTM standard, this length is defined, its diameter is defined. So length is 50.8 mm, 50.8 mm, diameter is 12.8 mm, like that. Okay. So you can see it's not that long. 50 mm of length is not which is going to be this large, right? So small, 50 mm. So this is about the specimen. This specimen will be of what material? Of that material for which we want to know the safe stress. I want to know if steel, a specific type of steel, how much stress it can take before it fails. So what will I do? I will need the specimen of that material only. If I want to know how much stress aluminium can take before it fails, so I need the specimen of aluminium only. So dimensions to be discussed, but material will be the same for which we want to know how much will be the safe value of stress. Got it? So this is going to fit here, and then we are going to apply the load, and then we are going to do all the measurement. So what we are going to do, as a result of this movement, a load is being applied indirectly. We are basically elongating it. So it is going to resist, this specimen is going to resist the movement, which means internal stress will be there. So a load will be required to overcome that resistance. That load is P. As you can see, here the length was L0, here the length was L0 initial length or gauge length, but now it is L. Why? Because it has changed now. You are elongating it. So L0 has increased to L, right? So how much is the total deformation? Total deformation. Deformation is L minus L0. You can write it as delta L or simply del. Correct? So P value and del value, these are the two fundamental values for this test. Yes, you can calculate stress and strain from this value, but that is a separate discussion. Means we will discuss that after concluding this. But the main thing, the raw data which this machine is going to give you is the value of del and the value of P. Something you may have to calculate on your own. For something machine may have set up. For example, P machine can set up. P machine can calculate how much load is being applied. But in some machines, the del value is not directly calculated. So for that, L0 you already know, and after just few movements, you have to constantly measure L between the points. Which points? Between the gauge points. As I was telling you, the specimen will have 2 marks there. In the specimen itself, there will be 2 marks. You are not able to see it in this image, but if you look closely, there is a dot here and there is a dot here, right? So those 2 marks are there, which are going to move away from each other as you keep applying the tension. So length between them is going to, length between those 2 marks, here also those 2 marks should be visible to you, this one and this one, right? So length between them will keep on increasing. So using external measurement, you can measure how much is the length. You subtract it from the original one and you will get the value of deflection or deformation, right? So deformation and load, these are the 2 raw values that you get from this tensile test. From that you can calculate stress and all. We will be discussing that, don't worry, that how we can calculate the value of safe stress. But these 2 data are the first data that you get from this machine, load and deformation. Got it? Now, what I am about to tell you, pay attention to it, because many students have wrong concepts about it. Look, in this test, many students think that we apply a constant load P, that this machine is going to apply a fixed value, a constant value of P, and that is going to elongate it. And then we are going to measure that for that value of P, how much is the elongation. That is what students think. Wrong. No, we don't apply a constant value of P. Some students think that we apply an increasing value of P, that initially P will be very small and slowly we will increase and keep increasing it till the material breaks. So initially P will be almost zero, so deflection or deformation also will be 0, and slowly we are going to increase the value of P and del value is also going to increase, and at the point it breaks, it fractures, it fails, that value of P we are going to use or utilize. So what they mean, what they think, that P is going to increase and we are going to continuously increase the value of P. That also is wrong. So P is neither kept constant nor it is continuously increased till the material fractures. So what do we exactly do? If you don't keep P constant, that also, sir, you are denying that no, P is not kept constant. And sir, you are also denying that you cannot increase the value of P. So what do we do here? We do not control the load. Load is not our input. It is not our input. Load is our output. We measure that how much load is required. So what is input? Input is this, the speed with which you are deforming. that is kept constant. Listen again. We do not apply a constant load, or we do not apply a increasing load. We move this at a constant speed of, let's say, 1 mm per minute. In 1 minute, this crosshead will deform the material, will deform the specimen by 1 mm, or maybe 2 mm per minute, or maybe 3 mm per minute. It can be different. It can be different. That is not the main thing. That is not the main thing that you need to remember. Main thing to keep in mind is that what we control, what is the input, is this crosshead is going to be moved in such a way that the material deforms at a constant speed. Or in simple language, you can also say that we move the crosshead at a constant speed. In simple language, both of these things are slightly different, but that is beyond our discussion. You can also say that we control the crosshead speed. Crosshead is moved at a constant speed. Not load is applied at the same value, or not load is increased. That is our output that we measure. But what is the input? That this crosshead is moved at a constant speed, or in other words, we make sure that the specimen deforming at a constant speed. That is our input. That deformation will be happening at a constant value, at a constant rate. That in 1 minute it is going to deform by 1 mm. In next minute, more 1 mm more deformation will be there. In third minute it will deform by 1 mm more. Got it? What I am telling? This is what we are controlling. And what we are measuring then? Then we are measuring to do that, to achieve that. How much load is required? How much load is required is then going to be measured. It may increase, for some cases it may decrease. We don't know that. That test will tell us. That test data will tell us. But this is not what we are controlling. This is what we are controlling: rate of deformation, and specifically rate of deformation, not just deformation, rate of deformation. That for first minute it should deform by 1 mm. In next minute, after 2 minutes, total deformation should be 2 mm. After 3 minutes, total deformation should be 3 mm. This is the speed that we have to keep. Speed of deformation is what we control. The movement of crosshead at a specific speed is what we control. And then we measure. This machine has load cells to measure load required. To continue that, to continue this speed of movement, this speed of deformation, how much load we will need, that is measured by load cell. And that data is written here. It may be constant for some duration, then it may increase, then it may decrease. That we don't know. That test data will tell us. But we know that we will deform it at a constant rate. That per minute deformation should be 1 mm or maybe 2 mm, whatever is the parameter that you have chosen. This is so much important for you to understand, because many students keep thinking that we apply a constant load or we apply increasing load till it fails. Not at all. We do not control the load. We do not control the load in a way that is not our input. This is our input. No matter how much load is required, we don't care. We will make sure that it moves at a constant speed. The deformation is happening at a constant rate. And for that, sometimes it will require more force, sometimes it will require less force, sometimes same force will be required. That we will see. Understood? This is one of the most important things of this test that many students do not know about, and that is why when we go into advanced discussions, we are going to enter into very advanced discussions of this test, and at that point they start getting confused. So if you understand this, your understanding will be a lot better. Now, the P and del data that we are going to get from this test, it is useful, but directly we cannot use it anywhere. Suppose if you want to draw a graph, of load and deformation, right? You see, I have kept deformation on x-axis and load on y-axis. Why? Can you think? Because this is what we control and this is the output. So we are controlling the rate of deformation, right? how much deformation is happening per minute, and we are measuring how much load is required for that, right? So this is why this is kept on x-axis, this is kept on y-axis. Small thing to note, correct? So coming back to what I was telling you, that load and deformation curve, we can plot the points, we will get how much is the deformation, how much is the load, these points. We can plot and we can draw a graph of it. But that graph will not be much useful. Load deformation graph is not much useful. Why? For the same reason that I have discussed, that why load is not that useful and deformation is not that useful. Remember, we have discussed this initially, that why in place of load, stress is a better indicator, right, of failure, and why in place of del, strain is a better indicator of elongation. We have discussed this already, I am not going to repeat that. Hence, rather than using the graph of P and del, a graph of stress and strain is going to be, a graph of stress and strain is going to be more useful. A graph of stress and strain is going to be more useful, because we have done this test for a specific geometry, right? In real life, the part that we are going to make, the machine, the big structures, the bridges, they will have different shape, they have different cross section, right? So in that situation, the value of P required for fracture will change. P, value of P, because stress is equal to P by A, which means P is equal to sigma multiplied by A, correct? So if 200 megapascal is the safe value for a material, 200 megapascal is the safe value, suppose, for a XYZ material. So what will be the safe value of load for that material? 200 multiplied by cross section. If 200 is the safe value for any material of stress, which means 200 is the maximum stress that it can bear, right? So how much is the maximum load that it can bear? This formula will give it. It will depend upon the area, right? It will depend upon the area. For this, area is defined, a specific diameter is there, 12.8 mm. But in real life, diameter will be different. There will be different machines, different structures. So how much load it can bear is multiplied by, area is multiplied by safe value of stress. But area will keep changing, so safe value of stress will keep changing, right? This is not a property of a material. P, safe value of load, is not a property of a material. It depends upon the dimension as well. It depends upon material, but it also depends upon the dimension, right? So in real life, dimensions will change. So this is just a specimen. Real life things will have different shapes, different sizes, right? So the value of P and del that you are getting here, and if you plot it here, it will be of no use for any other shape. Hence, I am just repeating, I have already explained why sigma is more important than P, why epsilon or strain is more important than del. I am just repeating that in a different way by connecting it with the specimen, right? So that is why P and del diagram will be of not much utility. Stress and strain diagram will be of more utility, because stress is irrespective of what is the dimension. Per unit area only you are telling, P per unit area you are telling. So whether area is 10 mm square or 1000 mm square, it does not matter, because per unit area you are telling, you are dividing the area, and per unit area how much load it is bearing, that it is telling. Formula itself, P by A. Same goes for strain as well. We have already discussed this. Consider this like a repetition or revision of what I have already told, right? So that is why P del graph is not much useful and stress strain graph is more useful. Clear? Now is the main thing. If you want to find out the value of stress from P, means what you are going to do? You will divide that with the area. Divide that with the area, right? Similarly, if you want to find out the value of strain from del, remember this del is same as delta L, right? Both of the notations are same. So you will divide that with the length. But here is the problem. The problem is that length, or just consider the gauge length only, this is not same, it is changing. This is L naught, but this is L, this is L, correct? Length has changed, right? Change is small at this point of time in this diagram, but it is there. Same goes for cross section as well. Here you are not able to see it, but this cross section is different than initial cross section. Let's say initial cross section is A naught and this is A. So it is going to change. And what will happen? How it will change? Any intuition? Any intuition? Any feeling about it? When you elongate something, the area reduces, right? Have a look at this video here. In this video, a rubber band is shown to you just to give you a feel. I know that the materials that we are going to deal with are not going to be rubbery materials. So the change of dimension will not be as high as change of dimension of rubber. But essentially this is going to happen. When you elongate a rubber in one dimension along longitudinal axis, along transverse axis, its dimension reduces. So when you elongate a piece of rubber along length, along longitudinal axis, so along the transverse axis, its dimension reduces, right? If this is a stretchy material, a rubber, let's say, so when you increase its length, the transverse dimension is going to reduce. It will get shorter from that dimension, right? I am right now only discussing about the intuitive feelings. Don't think that how and why it's going to happen. We are going to discuss that. There is going to be a separate topic where we are going to discuss, we are going to relate them mathematically. We are going to do that. Right now, I am just trying to link your intuition and feeling with the explanation so that we can proceed on right now. Later on, we are going to come at this explanation, right? And more, we'll discuss more about that. So when you elongate along one axis, along length, along the perpendicular transverse dimension, it is going to shrink. So same is happening here. When it is getting elongated, so length is increasing, so cross sectional area is going to reduce, right? So here is the issue. Coming back to our discussion, what is the issue? The issue is that what area are you going to take? Initial area is different, and at every instant as you will keep on elongating, keep on applying the movement, the strain, the deformation, the area will keep changing. Same goes for length as well. It will not remain L naught. Initially is L naught, but it will keep changing to L. So now what you are going to do? There are two approaches here, and these two guys are discussing what approach to use. This one is a true scientist. What he want to do? The true scientist want to use the actual values. He's saying, I am a true scientist. I will use actual values. At every instant, wherever we are measuring, movement is happening, and after few minutes or seconds, we are taking the measurement. So this true scientist is saying that I will use actual values at every time, at every instant, whatever data is there, I will record their length as well, their area as well, at every reading that I am taking. And those things I will note, and I will use the actual value. So to find out the stress, I will use actual instantaneous. Let's call this instantaneous area, instantaneous length. At that instant, as I told you now, after every few seconds, after a few minutes, we are taking a reading such that the value of del is increasing at a uniform rate. So after in every reading, it is taking, the true scientist is using whatever is the area. It is measuring the diameter, from that it is calculating the area, it is measuring the length, which is putting here and then putting here to find out the strain at that point of time. But here is our engineers. What is the engineer guy saying? Saying, I am an engineer, I will simply use practical values. What are the practical values? This person is saying, I do not care about instantaneous area. I do not care what is the instantaneous area. I will simply take the initial area and initial length. I will simply take the initial area and initial length A0 and L0 in the calculation. I do not want to take instantaneous at every reading, note down the value of A and L. Like an engineer, I don't want to do the complicated thing. I will use what is practical. We will see which of them is better, how they are going to differ. It's going to be a long discussion, very long discussion. We will draw graph for both of these approaches. We will discuss that graph in detail. But at this point of time, you should know the fundamental difference in these approaches. So the value of stress and strain that we will calculate using this approach, where we will simply use initial value. Practical value means initial value. I have just written simple English here. You don't need to draw this or write this. I am just telling you for your own understanding, to explain it in my style. So this is practical value, means simply initial value. So when you use the initial value of area for calculation of stress and initial value of length for calculation of strain, this stress is called as engineering stress. This strain is called as engineering strain or conventional stress or nominal stress. So engineering or nominal or conventional stress means load divided by initial area, and same for strain. Engineering strain, nominal strain or conventional strain means deformation divided by original length, initial length. On the other hand, the true stress strain is sigma T. We are writing T to represent true, is equal to P divided by instantaneous area, or for strain it is this. You see, expressions are same, only difference is initial area and area at that instant whenever you are measuring, which will keep changing, right? Initially it will be equal to A0 only initially, but as area will keep on changing, this area will keep on changing, and obviously this stress will change. So stress will change here also. Don't think stress here will remain same. Even though area is same, but P is going to change. You will see how it changes, right? So don't think that okay, if area is constant, stress will be constant. This is denominator, but numerator will change. To deform it at a speed, at a constant speed, how much load is required, that P value may keep changing. So stress will keep changing there as well. Don't think stress will remain constant. Stress will keep changing in both of them. But one is using initial, original area, original dimension, original length, and other is using instantaneous values at every instant. Now, when you plot these, plot what? Stress and strain. Remember I told you P del is not going to be the P del diagram, is not going to be much useful. Load deformation diagram is not going to be much useful. We have to draw stress strain diagram. So eventually whatever value of stress and strain we are calculating from the value of P, from the value of del, that we are going to plot in a graph, in a stress strain diagram. But now both of them are not agreeing. Both of them are using different approaches. So we have got two separate diagrams. We have got two separate values of stress and strain. Hence, there are two separate stress strain diagrams. The stress strain diagram, one is engineering stress strain curve, other is true stress strain curve. Do not draw it. Do not draw it at this point. We are going to discuss this in so much detail. Each and every part, why this is going up, why this is constant, why again it goes up, why it comes down, why this continues to go up, the true one, all of it we are going to discuss in detail. You don't have to draw it. I am just giving you a flavor of it, a taste of it, that this is how they are going to vary, where we are using initial area is going to move like this, which is called as engineering stress strain curve, and where we use instantaneous values is going to move like this, which is called as true stress strain curve. Now let us discuss these two curves in detail in the next lecture.